Good afternoon, everyone. On behalf of the Department of Physics, I welcome all the participants to this 2 days international webinar on the topic MRI and normal spectroscopy. I am Dr. Valliaman, Associate Professor in Physics, Arulmigu Palaniandavar College, Palani, welcoming you all. I express my gratitude to our management, Principal Dr.Anbuchelvan, and Head of the Department of Physics, Mrs. P. Umarani, who gave concern support to coordinate this live video conferencing along with my colleague, Mrs. A. Shanti, Associate Professor in Physics, APS. Now, let me extend my warm welcome to our resource persons, Dr. Anbuchelvan and Dr. Rajabandian Paneer Selvam. Welcome, sir. For today's session, the presentation will be given by Dr. Anbuchelvan, researcher, Department of Chemistry and Biomedical Sciences, University of Hull, UK. We are very much pleased to invite him to present this session on the topic of science behind magnetic resonance imaging. Welcome, sir. Our resource person, Dr. Anbuchelvan, has completed his PhD in organic chemistry at University of Madras. He got many fellowships, awards, and honors. He has been visiting researcher to various reputed colleges and universities in India and abroad. And he is a member in many professional organizations and he has peer reviewing experience in many journals. He has been ambassador for outreach programs in various colleges and schools in UK. As champion in Marie Curie Association, he conducted several career development programs. The real value of education exhibits itself when one extends its application to the society. Our resource person, along with research activities, involves himself in society-oriented services also. He has conducted breast cancer awareness campaign programs among more than 20,000 village women folks in Tamil Nadu. He received Young Achiever Award and Scientific Tamil Award from Korean Tamil Sangam for his contribution in promoting science through Tamil as write-ups in YouTube like social media. Today's topic is MRI, as most of us know, as an acronym for magnetic resonance imaging, and it is a medical diagnostic technique. So this is the apt time for all of us to know more about the science behind MRI. So let us welcome Dr. Anbuchelvan to present his lecture. So please start your presentation. Thank you, sir. So this is the apt time for all of us to know more about the science behind MRI. So let us welcome Dr. Anbuchelvan to present his lecture. Sir, please start your presentation. Thank you. Sir, are you in the line? Sir? Hello, sir. Good afternoon, sir. Hello, sir. Can you hear me?
Yeah, ma'am. Just now only I'm hearing you.
Oh, you couldn't hear before?
No, just now I'm hearing you, ma'am.
Oh, sorry, sir. There must be some mistake.
Okay.
Shall we start the presentation, sir?
Can you hear me, ma'am?
Yes, sir. Hello?
Hello? Hello?
Hello?
Yeah, just now I'm hearing, ma'am, but I can't hear you for
Oh,
long.
others, I don't know whether others will be reaching up. Sir, start from the introduction.
Yeah, just
Ah,
let me keep my. Now can you hear me, ma'am?
yes, sir. Hello, audience.
Hello.
The presentation starts now. I request our resource person, Dr. Anbuchelvan, to deliver his lecture. Sir, please, sir.
Hello, ma'am. I think
Ah,
it's not working properly.
now I can hear you, sir.
Okay,
Hello,
ma'am. Just okay. I can hear you, I think. Okay.
hello, everybody. The presentation starts now. I request our resource person, Dr. Anbuchelvan, to deliver his lecture. Please, sir.
Yeah, please. Yeah, just let me share my presentation. Before that, I would like to thank you for the invitation for this wonderful opportunity to give the deliver the lecture on my current research in the uh, topic on MRI contrast agents for the early detection of the breast cancer. So, however, I would like to present just the basic science behind the MRI as a magnetic resonance imaging. So, let me share my. Yeah, just can you hear me, all the people? Is it okay?
Sir, they are in unmute form. Yes, sir. Yes, sir.
Okay. Okay, thank you. Yeah, just let me start from the. Yeah. Good afternoon. Actually, this morning is for me. It is the morning. So for me, it's a good morning. For you all, the people from India, is a good afternoon to everyone. My name is Dr. Anbu. I'm from India. I'm from same Tamil Nadu, and also I done my PhD in India in the University of Madras. Then I moved Indian Institute of Science for my first postdoctoral research. Then after I moved to as a FCT fellow to Portugal. Then I got Marie Curie fellowship in the with University of Birmingham. There I did some bioinorganic chemistry. Then I moved to University of Hull. Currently I'm doing some biomedical imaging research. Just I'm developing some manganese-based MRI contrast agents for the early detection of breast cancer. So just let us see the what are the things that I would like to things in the later slides. So this is the first one, the slides with showing as a pre-contrast and post-contrast. Some the profile is the in vivo profile. We have achieved recently in the healthy mice. So there it's a lung and liver and kidneys without adding any contrast agent and with the contrast agent. So it's showing we are getting some clear image of this This is the recent achievement. Based on this, just I would like to percolate the science about magnetic resonance imaging. So what is the exact science, what is the exact physics and chemistry behind that, and what is the role of the MRI machine to diagnose the disease? So then everything we will just let us see in this webinar. Everything I think I would like to cover all these things. So let us start from the history of some imaging. So we know that maybe in the early 18th century, I mean before the 18th century, so there was no machines are available to diagnose anything if it is happen inside the body. It's not possible because of, unless if you want the people should cut the body, or then only we can come to know what is something is, if it is happened any fractures or something, if it is happened is maybe abnormalities in the body, and everything could not be diagnosed easily without doing any operations or if you use surgery at all. But after that, we know in the year of 1895, Professor Roentgen was discovered a new kind of technique is called X-rays. We know that why it's named as X-rays, because of the name is due to the unknown rays. This may be a high potential of ionization, ionizing potential that rays possess. Because of that is that rays was named as X-rays. So after discovery of this X-rays, it was possible to diagnose something in the body, like is a fractures. For example, this is the good one. There was the metal and the hard muscles, the hard cells, like hard tissues are, it's made up of calcium phosphate or calcium sulfates. So that is made up of bone. The bone cannot this X-rays cannot penetrate the hard cells or hard tissues like bones. That's why after passing through the X-rays on the bone, then it will reflect it to back. Then that we are utilizing, we are converting into the signal that is called X-ray images. So because by using this X-rays, then we can able to diagnose something if it is happening, some fracture or something, some metals, if someone is swallowed inside, then everything can be easily diagnosed by using this X-rays. However, this is so harmful because of, we know that our body is made up of thousands and thousands of organic molecules, particularly biomolecules, proteins. Then everything's all the biomolecules are prone to ionization. So because of that ionization, then body will be soon it will be there is a possibility of the mutations that will cause cancer. So because of the recent days in India, there are every 10 minutes there are the 2 women are getting breast cancer, and also among the 2 women, there one woman is dying every 10 minutes. That is the current rate of the mortality due to the breast cancer. The breast cancer is mainly due to this kind of, this is the X-rays, also continual diagnosis through the X-rays is causing this kind of breast cancer. That is also the one of the main factor that inducing the mutations in the body. So just now we will come to the next one. Then this is the basic medical imaging machine that was discovered in the last century. Then after that, in the 19th century, there was the many imaging machines have been developed. However, those imaging agents are based on this kind of harmful radiations like X-rays. For example, you know that is a CT scan. CT scan is basically it's working behind the X-rays only. It's the X-rays only the source of computer tomography. Then after that, there is, you know, that is one more PET scan. It may be it is emerged in the year of 2010 from India, because of maybe before that there was only one machine available in Hyderabad, one of the Apollo hospital only. There was the machine is called PET, and now lots of people were died due to the cancer because of before in the proper diagnosis in the proper time. So that is the the PET also it's working on the based on the nuclear medicines. So all these nuclear medicines, that is we are injecting some isotopical atom material that we are injecting, that is called a nuclear medicines. So that nuclear medicines also is harmful to our body, even though it's producing some beta rays, so or like gamma rays or something like without ionizing radiation. However, it is harmful to our body. So just see after that, after discovery of those things, then there was in the year of 1947, the professor Felix Bolz and Edward Mills Purcell were discovered a new kind of machine called magnetic resonance imaging by using a simple non-harmful radiative materials energy, the sources, that is magnetic energy and radio waves. So these, we know that magnetic field is not harmful, and also this the whole, I mean the Earth globe is also is nothing but is a magnetic in nature. So we know we are in the magnetic field. All the people we have there is the magnetic field around our body. There was some myth also going on in our Hinduism. So now we will come to the next part, is the first clinical MRI. Then after that, in the year of 1977, by Paul Latterber and Peter Mansfield and Raymond Damadian. So these three, some physics and including the biological science, use this MRI as a diagnostic agent to diagnosing something, if it is what is inside in the body. So by using the MRI, they have diagnosed. So then after that, there was emerged as several new kind of machines, everything. So just we will see in the later slides. So just let me start. What are the main principle of MRI? It's all about strong magnets. It's full of about magnets. So we know that in the world is nothing but is the full of the geomagnetic strength is around 2.5 to 6.5 into 10 to the power of minus 5 Tesla. It means very in the power of 10 to the power of minus 5. It may be 0 point after 40, then 2.5 to 6.5 Tesla only. That is the whole Earth's magnetic strength. Then that is we are measuring in the Tesla. But then the NMR machine, we are using the magnetic power is around 1.5 to 3 Tesla. It's maybe around 5,000 to 1,40,000 times stronger magnetic field we are creating, we are applying on our body. Then only that will allow to diagnose what is happening inside the body. So we are sending that much amount, maybe more than 1 lakh times of magnet strength only we are sending inside the body. So just what is exact, how much energy can be sustained by body? Normally, this is the, because of we are creating this is very temporarily. So within half an hour or 1 hour it will go off. I mean we are sending the fluctuation of the magnetic field to the body. That's why it won't create any much problem in the body, and sometimes it may cause some dizziness. Maybe our body can sustain only 10 I mean around 1.5 Tesla is a minimum amount of energy is required. Otherwise it will make some dizziness, but that is also a temporary, it's not permanent. So that will be this indicates that this is the good machine to diagnose all the things. Even the body functions also we can diagnose, and also some disease progress also we can diagnose. Just I will let us see in the further slides. So just what is the strength, then how do we can compare? That we are using very harmless source is a magnetic field and the radio frequency radials or radio waves. So just how much amount of energy. Someone is making noise, please close. Yeah, okay. So thank you. It's a method in Tesla. Just to, I already said is the method in Tesla, and we are using the clinical MRI is in the range is 1.5 to 3 Tesla, and also it's around 50K times. It may be approximately 50K times greater than the Earth magnetic field, and also this energy. So just if we are using this energy, we can able to pick up a car. See that there is a diagram. There is a picture. It's just picking up a car by using a strong magnetic field. So this much amount of energy we are sending inside the body. I said already, this is just 10 million milli Tesla is enough to that can sustain the body, that no problem will happen. But if you are going behind that, it makes some dizziness or something like, but that is also a temporary. So now we will come to this. What is the physics and exact chemistry behind the magnetic resonance imaging? Just let us start from some applications. We know that MRI, I said, is the MRI allows to visualize soft tissues, including muscles, brain, lungs, and internal organs, because it can penetrate everything, all the layers, because of the just how it is making images. That only we are going to see in the later slides. So now there is another important application of this MRI is able to diagnose and evaluate disease progress. I mean, from the first stage to the last stage till the metastasis, we can able to diagnose by using this MRI machine. So, and also some brain function. I mean, from time course MRIs also is emerged now. So that also will be now. It's we are harnessing to understand how much what is the real function inside the human brain, and everything we can come to know by using the MRI machine. So now the next, so how does it works? So just this is the based on the principle of NMR. So we know all of the most of the people we are here is we know we are familiar with the NMR technique that allows to elucidate the physicochemical information of certain molecules, particularly hydrogen containing organic molecules. We know all the protons. So why what is the exact NMR? Just let us review the NMR techniques. So we know that this is the sample holder that is covered by a radio frequency coil that is, and also that is surrounded by the strong magnetic field that is cooled by liquid nitrogen or liquid helium. So that makes the system is a very strong magnetic, I mean super magnetic field. We are creating the super magnets around the coils. So radio frequency coil, because of just now let us see that if you are placing an organic sample, for example, if you are keeping any methanol or ethanol or whatever it may be, any organic compound, just if you are keeping inside the sample in the solution of deuterated solvent. So after passing the radio frequency, after just we are started to send the magnetic field, so where there is the proton. I mean, why we are considering the proton? Because the nucleus has some spin. We know that any charged particles, they can have their own spin and they can revolve around their own axis. So because of that, the charge, they are started to spin. Because of that, we need the nucleus spin to diagnose the molecule. So the spinning is depends upon the environment, particularly the chemical environment. Similarly, so when we are passing the magnetic field we are sending the magnetic field, the external magnetic field to the sample containing proton get excited. They are started to magnetize. The magnetized means they'll align with the magnetic field. Sometimes they will oppose with the magnetic field. But when they are aligning with the magnetic field, that is called magnetized state. So otherwise, then just we will come to the exact physics. There is that is a magnetic moment and also angular momentum, because of the proton has the mass. So because of that angular momentum, this proton can start to spin like a top. So that is called a precessional frequency. So if it is magnetized, So then it needs some amount of energy to undergo excitation. What is meant by excitation? So just let us compare with a cup of water. Just you take the cup of water, is the now just you can touch that, because of that is in the room temperature, that is nothing, no more energy in that. So just the same cup of water, just if you are keeping on the stove and is just supplying some amount of heat energy. So when you are supplying heat energy, they will undergo hot, they starts to boil, maybe few minutes. If you are heating, then it starts to boil, but now you can't touch. But when you put off the fire, then immediately that within few minutes it will come back to the original state by losing the absorbed heat energy to the surroundings. That is the basic thermodynamics. Similarly, here, if you want to make the water into their excited state, you want to supply heat energy. Here in the proton, you need to excite any proton in the magnetized proton. You need some amount of energy, that is nothing but radio waves. I mean that energy is enough to excite the proton from the lower energy to the higher energy. So when you stop when you are sending the radio frequency radiation through this radio coil, so that is called coil. So when you are sending the energy to that, then proton get excited. When you stop the radio frequency or radio waves, then it will come back to the original state by losing absorbed energy from the radio frequency. That energy we are converting into detector and amplifier, and it is giving us NMR spectrum. So then we can come to know which proton is where. It is according to its chemical environment. Then we are elucidating where the proton is situated in the molecule. Everything we can come to know by using this NMR technique. Just instead of the organic molecule, instead of any chemical sample, we are placing our body inside the same environment. I mean the radio frequency coil. This is the blue color is the radio frequency coil, and this is the magnetic field around that. So when we are keeping that, our body is containing protons can get excited, get magnetized. It may be the two ways of magnetization. We know that one is along the external magnetic field, that is called longitudinal. If it is perpendicular to the external magnetic field, is called as transverse, or X or Y direction is perpendicular to the external magnetic field is called as transverse magnetization. So if maybe the protons get magnetized, so then after that we are sending the radio frequency radiation, they will undergo excited state. Then while you are stopping the magnetic radio frequency radiation, then it will come to the original state. Then that is only we are making into a simple images, that only MRI images. Just now we will come to know what is happening inside the body. So now we will come to the next point. So is nothing but imaging water. So where is the protons are available in the body? We know that the world is the whole world. There are all the religious people will say the world is made up of 5 elements. We know that everything is made up of the 5 elements: the water, Agni, those kind of things. So the same thing it is happening in our body. So the 70% of the human body is made up of water. So all parts except the bones, all the tissues has a different amount and different types of water in the different forms. So in the body, so that we are on the MRI machine is targeting such kind of water only. So the MRI machine is nothing but imaging water. So just let us see the further. Just we know that all the organs there is listed here. How much percent of the water is present in each organ is listed here. So just we are taking only one water molecule from that. Just we need to understand what is the exact science behind MRI. So here is just water molecule is made up of 2 hydrogens and 1 oxygen. We know the oxygen is made up of is even number of electrons and even number of protons and neutrons. So it's not susceptible to the magnetic energy. So just we were considering only 2 hydrogens. So now onwards we will say this as protons, because of this we are going to consider the nucleus spin. So we are going to inducing the energy of a nucleus, I mean particularly proton, because a hydrogen has only 1 proton in that. So we know that 1 electron, 1 proton. So just this is the exact structure. We know that it's all the proton is positive charged. Any charged particle can behaves like a tiny magnet, and also they starts to spin on their own axis. That's why I represent here as a spinning proton. So what is a spinning proton? What is happening in the spinning proton? So just only 1 second, just imagine, just only 1 second, if you are applying 3 Tesla of the magnetic energy, it starts to within 1 second, each proton can rotate around 63 million times. Maybe is we can't imagine that much speed. Each proton is just rotating within only 1 second. Can you hear me,
sir?
Okay,
sir,
yeah,
your PPT presentation is not seen.
Sorry, you can't understand, mom. Sorry, you.
Sir, your PPT presentation is not seen in the screen. The slides are not seen.
So till this time, this only, ma'am.
Okay, sir. Okay. No, the slides are already. No, your face is. We can see your face, not slides.
Oh, till this time it's happening same.
No, sir.
Okay. Now it's okay, ma'am. Are it's okay or?
Sir, your talk only now, or slides will be also displayed?
Sorry, I can't understand. Now it's okay or do it something?
So it's okay, sir.
Okay, yeah,
Sir,
someone is saying
sir.
this. Okay, yeah, just let me.
Okay, sir. Now.
Yeah, just this is the proton. This is 63 million times within only 1 second. Each proton is it's very fastly it's rotating, as it is spinning within 1 second. That much speed of the proton. So it means in the 3 Tesla, this starts to spin on there and magnetize. It is around 63 times. That is why we need to send around 63.9 megahertz amount of radio frequency is needed to excite the proton from the lower energy to the higher energy. So when they are sending that, it starts to absorb the energy and they starts to precise around their axis. So this is we need. Then when we stop, then it will come to the original state that we will come to. Then the next slides we will come very clear. Will come to know very clearly. Just I will show here. So then we can get the signal of whatever the energy absorbed during this. According to the different environment, the protons can absorb different amount of energy. So then we can come to know which proton in which tissue, where the normal or abnormal, and everything we can diagnose by getting the exact images. Now, so T1 until T2 relaxations. What is meant by T1, T2? I said already, it's maybe the proton is aligning along the external magnetic field, that is called a longitudinal. If maybe the proton is perpendicular to the external magnetic field, is also known as T2 relaxations. So just we will start, just to let us learn the longitudinal and the transverse relaxations. Just we hear this, I said there is a proton is just aligning in the along the external magnetic field, that here there's a proton in the Z direction. Here in the X or Y, just I consider here is a Y direction. Just here this a perpendicular to the external magnetic field is also called transverse relaxation. Now I start to send the energy. So what happens when I start, I said, so if you want to excite the water, we need to send some amount of heat energy. Similarly, if you want to excite the proton from the lower energy to the higher energy, we need to send a minimum amount of energy from the radio waves. It's called radio frequency. Just we are turning on the radio frequency, the proton is just flipping to the perpendicular. I mean around the 90 degree is flipping. If maybe sometimes if you're sending for long time, they may flip around the 180 degree also. That is a possibility. So the 180 degree, it will come up to here, that is opposed to the magnetic field also possible. So here mostly we used to do is just we will make the proton to flip up to just 90 degree. So here also this is the proton. Now it's a flipping. After turning on, it starts to around 360 degree. Maybe it's split to 190 degree. It will come over here. Then afterwards, it will come back to the original state by. So this is the spinning. In some directions, they are in around 360 degree. They are flipping in the different angles along the x-axis, particularly perpendicular to the external magnetic field. Now, just what is happening if you turn off the radio frequency radiation? It will, when you turn off, I said already, it will come back to the original state by losing absorbed energy to the outside. So see, it's coming back to the, I said there are the 4 lines, 4 arrow marks I put here. It means that everything is coming back to the original state. So now, how we are getting the image? So this is called the relaxation timing. So from the flip angle from the Y directions to the Z direction is taking some time. It will take for the flipping. That time per second is nothing but T1. The time needed to realign with Z axis in the magnetic field is along the magnetic field is called as T1. I mean longitudinal T1. I mean relaxation, spin lattice relaxation. I think already some people, if you are doing some research in the NMR, then you come to know that is what is meant by spin lattice relaxation. So now we are getting, so just we will turn off this perpendicular to the axis, I mean the transverse relaxation. It will come after flipping into all the different angles, and then it will come back to the original state, that is Y. So just the both, so from T1 we are getting this, just if you are bisecting from top to bottom of the body, from the head to tail, just if you are bisecting, then we are getting, this is called T1 weighted images. So now if you get this, if your cross section, we are getting the image. See, there is a small yellow color spot is due to some cancer. So just that is indicating the cancer, how they are imaging the cancer in the brain. So this is the T2 weighted images. This is the basic of basic science behind the T1 and the T2 relaxations. So now just we know now we don't want to think anything about the beyond this, because of just I'm saying about using contrast agents. Why we need to use the contrast agents? Because of we know we heard something, so the chemistry is also playing important role in the MRI science. Reason, because of most of the time in the body, both the T1 and T2 relaxation times difference is very the same. Always very subtle difference only we are finding. I mean, sometimes, I mean, most of the time, it's not often we are finding only the very subtle difference between the normal and abnormal tissues of amount of water and the tissues nature and everything. For example, if there is a tumor in the breast, So we this cannot diagnose easily if you are using simply a MRI machine. It cannot diagnose exactly what is the cancer and what is the tissue with cancer and tissue without cancer. So sometimes it's not we can't we can mislead the diagnosis. So for that only we are using a new technique, that only we are approaching the chemistry people for the support to develop contrast agents. So the contrast agent means we are going to get a very enhanced image. So that only my research, the current research. So just let us start from the contrast agent. There is a chemistry behind the contrast agents. So this just we are seeing some the figure is the flower is the flower behind there is something we don't want that part. The behind there is something we don't want that. So we need the image of the flower means just we are doing the contrasting by just chemical computational. Just a very simple, just we are expanding, we are only targeting this flower. So that is a possibility by doing chemistry also, by using the chemical agents. So we can extend, we can enlarge, or we can enhance the clearance of the figure, and particularly in the inside of the figure we can easily diagnose normal, and we can easily distinguish normal and abnormal tissues, particularly cancer and brain functions. So just this is the uses of contrast agents. Just let us see an example. This is the MRI image, MRI, I mean magnetic resonance image without the contrast agent, that is represented by CA. So here is you can't find any, there is no much information that we except just this is the brain, this is the eyes, and these things only we can able to find. But we don't get any clear information from this image. So but it's the same the people. So if you're using the image with, this is the image with contrast agent. See here, there are the lots of difference we can find here. There are the some tumor particles and everything. I mean something like a flake materials are present in the image. So this is the feature of using contrast agent in the MR images. Just we can go for the further some chemistry behind that I'm currently what I'm doing. So the benefits of MRI contrast agents, just how the principle, what are the benefits? MRI image relies on their distinctive signal intensity to adjoining. We know that normal and abnormal tissues, that is T1 and T2. And however, the relaxation times of normal and abnormal times are frequently overlapped. So abnormal tissues cannot be diagnosed. So, and also the shortcoming is overcome by contrast agents, which alter the tissue relaxation times
excuse me,
and manipulate. Yeah, madam.
So for some people, the PPT is not visible, sir. So can you click again, present now?
Okay.
And the audience, please, you pin.
Yeah, madam. Yeah.
Yes. How it is?
Is it okay?
No, sir. The PPT is not visible. Sir, go to the Google Meet and you press the present now button.
Okay, ma'am. Just
resume.
Sir, press the resume your presentation, sir.
Yes. Yes, madam.
Audience, please pin.
Pin this presentation.
Audience, please pin this presentation. Yes, sir, please. The PPT is not yet visible.
Just a minute, madam. Just
audience, you please pin the presentation.
Now it's okay, ma'am.
In my system is available, but for some people. Yes, sir. It is now. It can be seen. Thank you, sir. Please continue.
Okay, thank you. So just we'll see this, we can get very clear image by using contrast agent, I said. So just this is the symbolic representation of the contrast agent, how it's working. Just we will see this is made up of gadolinium. The gadolinium is, we know that atomic number is 64. It has 7 unpaired electron in its outermost orbital. Because of that, how outermost 7 electrons, that electrons can interact the water molecules in the body. So that is the very key, because of 7 unpaired electrons and the water protons can interact by dipole-dipole interaction. So the dipole-dipole interactions are induced by this the 7 unpaired electrons in the gadolinium, and also the gadolinium, because of that unpaired electron, it is a magnetically active. So that's why the gadolinium complexes are still, it's the more number of chemicals are, in particularly contrast agents, are made up of gadolinium compounds. So particularly, so just we can see there is only one water molecule is in the first coordination sphere. It's called coordination sphere because the water is directly bound to the gadolinium metal. That is very metal coordinated water molecules are very important key for the contrast agents. So here is the first coordination sphere. There is only one water molecule, and sometimes there is a contrast agent with the 2 water molecules that I will show you the later. What is the difference between the mono and di? So here is this is the first coordination. This is the second coordination sphere. Is there are some water molecule, the small water molecules present in the crystal lattice, or they are in the surround the molecule. That is called second coordination sphere. And third is in the solvent. I mean from the body or the tissue containing water. So what is going on here? I mean the magnetic compound, the magnetic material which is present. This is the brown. The brown is nothing but is not a water, is nothing but a chelate. Is a chemically is called, is like it can grab the gadolinium metal. They will keep inside. It is very tightly. It should not lose the gadolinium to out. So gadolinium should be in the chelated condition. It should be formed as a complex. It should not be a free gadolinium, because the free gadolinium cause very adverse effect, very toxic effect to the human body. So that's why we are making as a gadolinium complexes. So the inorganic chemists particularly, we are interested to develop, because the gadolinium complexes. So the gadolinium is tightly bound the only one water molecule. That water molecule is exchanged to the second sphere water molecules of the crystal lattice, or the surround by the molecule particular contrast agent, then that will be interact with the tissues of the human body. So the water can come here, then it will go, they'll come close to the molecule, then get magnetized, then it will go off. So because of that magnetization, they'll absorb the radio frequency radiation, then it will come to the original state, then it will give the exact image according to the environment, particular tissues environment. That is the basic science of the contrast agent. So now we will let us see some what are the effect of contrast agent on T1 relaxation. Just we know already this proton is lying along the Z direction. I mean is aligning with the external magnetic field. This is the ground state. So when you are turning on the radio frequency radiation, it flip into, maybe this here I shown is just 90 degree flipping into Y direction. So at the time, just I'm adding contrast agent. So without contrast agent and with the contrast agent. So without contrast agent, it is coming very slowly to this place. I mean, without contrast agent, it is coming very slow to back. I mean, it will take a long time. But here, I shown only this 4 lines. It means it's coming very fastly to the Z axis. I mean, it's the contrast agent induce the proton to flip back to the original state very fastly. That very fast flipping is caused by the contrast agent. how they are causing, I said in the before side, by interacting the protons from the outer spheres, particularly second sphere and the third sphere. It means there is a one water molecule should coordinate with the metal ion. That is the ideal for MRI contrast agents. So that is the why the time required is a longer T1. So this is taking very short T1. This contrast agents making very short. So what is the effect of longer relaxation and shorter relaxation? Just let us see in the next slide. Just this is the nice very clear image. I mean, if you're going shading, I mean the fade, the darkness is getting decreases and the brightness is increases. Now we will start from here. This is the longer T1 without contrast agent. So this is taking long time. See, just if we will consider here, so time, but it is here. So if you are adding the contrast agent, it will this line, the dotted line shows there is a very short time is enough to the state. So now this is corresponding is a clear image when compared to the contrast agent without the image without contrast agent. That is called long T1. This is the short T1. This is the basic one. Just we will see this exactly what is happening. This is the contrast agent without without contrast agent. This is the MR image, but because there is the relaxivity is overlapping, unable to distinguish normal and abnormal tissues. But if you see here, there is a if you're using the contrast agent, there will be a very clearly we can come to know where is the tumor is present, because this is distinguishes the normal and abnormal tissues. This is the effect of contrast agents on T1 relaxation. This is published by something nuclear medicines and MRI related books in the year of 2001 and 2019. Now we will come to the what are the clinically available manganese MRI contrast agents. So there are more than 10 gadolinium based contrast agents are available, but I shown here only just 4 of them. So these particularly these are the chemical structures. So mostly they are is maybe there's many people the EDTA and all those kind of things, and also this is called cyclum. So where the metal ion is present inside. And very importantly, you can see all the complexes have one water molecule is directly coordinated to the gadolinium. Is a gadolinium first coordinated. This is the metal coordinated water molecule. These are the ideal for the MRI contrast agent. So okay, so these are the common example, and also what are the other conditions, because the gadolinium should not be, the complexes should not be positively charged. I mean, the complexes should be negative. See here, 1 minus, 2 minus, 3 minus, 4 minus, but the gadolinium is always 3 plus. Totally, there will the whole charge is 3 plus and 4 minus. Totally, the whole charge of the complex is 1 minus. The minus charged complexes are very efficient to, they can penetrate the our tissues, particularly shells. They can easily penetrate when compared to the charged particles, charged complexes or charged contrast agents. So there are some points they have given R1. This is called relaxivity. See, 1 millimolar of complex, there is this much second is taking per second. This much compounds are getting relaxed. That is called R1, relaxivity value per second in per millimolar. This is 3.8. When compared to this, almost see 1 gadolinium, 1 water molecule, 1 water molecule. But this compound is showing around 6.8. So when compared to this is the very higher relaxed. I mean, more number of water molecules are getting relaxed when compared to this molecule. The reason is the presence of some hydrophobic unit. Hydrophobic unit means this is also hydrophobic unit. It means easily there is some organic moiety. We know that our body is made up of both organic and inorganic, mainly organic. So there's lipids and all the lipid bilayers and everything will be covered by the cells. So if you want to penetrate inside the cell, we need some amount of some hydrophobic or lipophilic moiety. That's why these molecules are showing higher relaxation. So now we will come to that next. So now the recent days, a new kind of MRI contrast agents are emerging. Particularly, they are called as responsive or smart MRI contrast agents. So just what are the responsive? This is see here the gadolinium complex is the zero charged. Here also zero charged because of 3 minus and 3 plus. It's totally zero. So now these both are acting as a MRI probe. But you see here there is a middle. There is a empty place. This empty place can selectively bind only calcium. So the calcium can bind here. So what is the difference between this? This is acting as both. This place is acting as a calcium receptor. We know that the calcium ionic radius of calcium ion and also gadolinium ions are almost same. That's why. So when you are injecting this kind of compounds inside the body, sometimes they can recognize the calcium. We know that the brain functions are mainly all the neuronal functions and everything is due to the calcium channels in the brain. So the calcium, if you are sending this, so they can respond wherever the calcium is rich in some biological molecules. They can absorb the calcium ion. Upon binding the calcium ion, say like this. This is the calcium ion is binding here. So this is the gadolinium chelator. Here is represented as a small like a oval shape with like eye. So now we will come to this is called phantom image. Phantom image is taken in the MRI machine directly. Just we are keeping the small sample vials. The sample vials are taking the photo in the MRI machine instead of the human body. Just we are getting the very bright image. So here this is the only the compound is not that much brightness, but this is the brightness is increased. This is the compound gadolinium 2. Here is when compared to this one, this compound is the highly efficient to bind the calcium. Upon binding calcium, it's showing enhanced brightness in the MRI. That is called the MRI phantom image. This shows that the compound is highly selective for MRI contrast, selective for calcium responsive MRI. So this is the new kind of compound. So I'm developing the same smart MRI contrast agent to diagnose early onset of breast cancer. My compound is selectively binding ATP. You know that this ATP is adenosine triphosphate. Just let us see in the later slides. Why manganese contrast agents best over the gadolinium? That is very important because of recent days the manganese. I mean, I said already the gadolinium should not be free, should not be a salt, should not be a gadolinium ion. It should be a complex. It should be grabbed by the molecule that is called gadolinium chelates. So that is the reason we always prefer to make the gadolinium complexes. That only we are harnessed as a contrast agent. That is however, sometimes some regions they are inside the body because of inside the body there are the different physiology conditions are possible. For example, if you go to the mitochondria inside the cell, the pH is it is decreasing up to 5. Is maybe the around 5.5 or something. It's maybe the very acidic pH in the mitochondria because there are the lots of amino acids are present in that. They are producing a new kind of proteins inside. So that is the reason the mitochondria is the one of the energy factory in the cells. So now on different conditions, sometimes the molecules, the chelates and chelate inertness will be very less. Sometimes they may release the gadolinium 2 out. So because of that situations, the free gadolinium ions causing a new kind of neurodegenerative diseases are nothing but deposition of gadolinium in the brain and other parts of the body, particularly the skin functions. It's showing nephrogenic systemic fibrosis. Because of that, there is in America and Europe countries, there are some of the gadolinium contrast agents are banned. See here. So instead of that, I'm sorry. Hello. It's okay. Okay, just let me go from the gadolinium, and also this is the next one. Is the I prefer to use the manganese because the manganese is the biogenic metal, and also it is also has 5 unpaired electrons in the outermost orbital that show equivalent MRI contrasting capability. That's why, and also it is safer than the safe alternatives for the MRI contrast agent. That's why I'm interested to develop manganese-based MRI contrast agent. So now we will come to here. So this is the very simple example that I have developed these two kinds of compounds. The one is, this is the very simple complex by using some template method I have developed. This is the manganese based contrast agent. So this shows excellent MRI profile when compared to these things. And also this is, I have added a 2-dipicolylamine. This is well-known ligand in the chemistry for binding zinc ions. So I mean, this compound can selectively bind the zinc. At the same time, upon binding the zinc, it will leave some vacant sites for the other anions. That's why I have used this molecule to probe the phosphate that is very important, essential for the growth of breast cancer cells. I mean, all the breast cancer cells are needed much amount of phosphate than the other sources of nutrients. That's why the breast cancer people, women, those who are getting some people are getting the breast cancer, the first metastasis into the next organ is the directly to the backbone, because there is the much source of phosphate. So my compound is selectively binding the phosphate. So upon binding, particularly it is selectively binding the ATP. I mean, ATP is adenosine triphosphate, is the energy source for the cell, is a currency, energy currency in the cells. So that can bind. Upon binding, it shows the both functions. One, this response to the ATP, at the same time it enhances the MRI contrasting capability. So that these are my compounds that recently, this is the crystal structure. So now this is the kinetic stability. That is very important because of, I said already, it should be, all the metal ions should not come out from the chelate, because of, if it is coming out, it will be a free ion. The free ion will cause a lots of adverse effects in the body. That's why we have tested around 60 days. So with a high amount, around 10 equivalent of the zinc. So there is the relaxivity is almost same, which suggests that the zinc is not replacing the manganese in the complex. And also this is the pH dependent studies. I have studied the 4 different pH. The relaxivity is not varied around 5.3 and 7.4. It suggests that the compound is highly suitable to use in the human body. Particularly, we have tested with the clinical MRI, and we have achieved some profiles, I mean in vivo profiles. Just let us see in the later slides. So this is the just the stability studies. We know there is routine studies just I have used from different days, and everything is suggests that the compound is highly stable. It's not dissociating into a free ion and a chelate. It is remain stable for long days. But actually the MRI contrast should at least within 1 day, 1 hour, or 1 to 2 hours. If it is stable, that will be enough. But my compound is more than a month. It is highly stable in the same solution. So now just the anion sensing. So I said already my compound is selectively binding ATP. This is one of the selectivity studies, and I have used different phosphates. See here, when I add the zinc and phosphate, the phosphates units are binding in the zinc, and the remaining adenosine unit of the ATP is binding the manganese, and shows enhanced image. Just that this is the binding studies that but this shows the high binding propensity of the ATP over the other phosphates. So this is the titrations. Just this is the relaxivity studies. These are the simple, the zinc bind compound shows higher binding affinity, and when compared to this, there is the ATP bound compounds are highly high relaxivity, shows a high relaxivity than the other phosphates bound complexes. So this is the relaxivity values and log K values. This is around 6.912 per second, millimolar per millimolar per second. So this shows that this ATP bound compound shows high relaxivity, that we can see very nicely in the phantom image. I mean the MRI machine we have taken. This is number one is the Magnavist. This is already available, clinically available in the market. If maybe some hospitals they are using this Magnavist till this date. This is a gadolinium based complex, but thus when compared to this gadolinium base, my compound shows highly brightness. This is the water. This shows only blue color. This is a bit orange, and we are going to see that the brightness is increases with the different compounds, particularly ATP bound compound shows high relaxivity around 10.860 per millimolar per second when compared to this without anything like a methyl compound, that we will see the later slides. So this is the compound without any dipicolylamine, is a free of zinc or free of ATP. This compound itself shows increases the brightness, and this when compared to the M is clinically available Magnavist. So this number 1 molar and 1 molar, this is the brightness is very higher than this clinically available Magnavist. So now this is the we have compared with the BSA. The protein is already some people knows that the BSA is important. I mean this is a serum albumin. This is a high degree of similarity of the structures with the human serum albumin, that is their drug carrier in the body. But for example, if you are taking some tablets, for example fever or something is in the body pain, if you're taking ibuprofen, or if you're taking aspirin, or if you're taking paracetamol, whatever it may be, if you're taking all the drug molecules should bind this human serum albumin, that only is present in our blood, that is carrying from all parts of the body. That's why this is the blood drug or material carrier. So my compound is strongly bind with the BSA, so it's showing enhanced brightness. So this is very useful to use in the blood plasma. That's why we have suggested that this compound is used as a blood pool agent. I mean, even in the blood pool, we can able to diagnose some what is happening in the liver and some other organs. So this is the complex that we have used. So we have achieved around 4.4 and 4.9. This is the suggests that there is the 2 water molecules. I mean, there are here actually the crystal structure. We got 1 chlorine and 1 water molecule, but actually the chlorine is replaced in the water molecule. It's forming bishydrated. That is, the bishydrate is a special of this complex. It's showing high relaxation than the gadolinium complexes. So now this is this is also some routine study, but just some specific binding plot I have achieved. Then that I have, this indicates that the compound is strongly binding with the protein, particularly bovine serum albumin. So this is dissociation constant, and N is also here showing that it's very, very strong binding that. So this is called a nuclear magnetic relaxation dispersion. This kind of studies are only done by only few institutions are available. Then I have collaborated with one of the very familiar, well-known scientists in the field of NMRD, particularly MRI research, Professor Mauro Botto from the Italy. Now the people just now they started back to the laboratory because of during this pandemic. It was very, very tough time, even though they have helped me to achieve this kind of profiles, particularly NMRD profiles. So this is the one. Currently, I'm collaborating with one of the Tübingen hospital in Germany, who is also a well-known emerging leader in the field of MRI imaging, particularly clinical MRI. Just he is using the rat, and we have used the very healthy rat, and this is the pre-contrast before adding the contrast agent, particularly before adding our MNLME complex. And after addition of this, it's showing some just as enhanced image. So that this is a difference. So clearly we can get particularly liver and kidney. So this my compound is selectively targeting kidney, and also this less amount when in the bladder. It means is particularly my compound is targeting liver. Maybe if it is coming to the bladder, it means all the compounds are coming very fastly to the things. I mean, it's getting clear through the hepatitis. I mean, hepatic clearance is nothing but is a clearance through the liver. So that my compound is selectively both kind of clearance. I mean, it's fastly. It's not staying in the body for more than 1 hour. It's coming very fastly to the body. Bladder means it's coming as a coming as a urine. I mean, my compound after showing the diagnosis within 1 hour, then it coming clearing out from the I mean healthy rat to the as a urine. That is a very great feature of this my complex. So now we will I'll come to the final stage. It's a summary. I have developed a new kind of manganese based. Just we have seen what is meant by magnetic resonance imaging, how we can how the T1 is works and the T2 works, and what is the basic principle behind the MRI, and also why we are using the contrast agents. Then what are the main metals we are using as a contrast agents to get the enhance the images. And also what is meant by responsive MRI contrast agents. Then I shown a calcium sensors. Then based on that, I also have developed a different kind of under new novel ATP sensitive contrast agent, that is zinc based and everything I have shown. So and which shows very high relaxivity with compared to the DPR, zinc or ATP free manganese complexes. So now, so this is my research collaborations. This is my current university. So this is the University of Hull in the UK. So this is my previous mentor. Now currently I changed to a different group. I'm because of my the situation. I got some postdoc question in different group. So now he got a postdoc. He got a lecture position. He shifted to his lecture position to the King's College of London. You know that the Prime Minister of UK, Boris, only he is working as a imaging field, molecular imaging chemistry department senior lecturer. And this is the government hospital in where I'm living. The city called Hull is called Hull Royal Infirmary Hospital. So where the Dr. Lawrence is standing near me. His name is Lawrence, and he is in charge of the MRI center, who is collaborating with me for this phantom images. I shown you some series of phantom images where I have acquired, particularly from the Royal Society, Royal to my the previous. This is my the past institutions. I done my PhD in India at University of Madras with Professor Kandasamy at the Department of Inorganic Chemistry, and with the senior CSI or SRF, and I got Kothari fellowship. I worked with an year with Professor Pathsarthi Mukherjee at the Indian Institute of Science. Then I got FCT postdoc fellowship with the well-known scientist in the European well-known scientist who is very familiar for electrocatalysis and biological in bioinorganic chemistry, particularly the catalysis field. So then I worked with 3 years with him. Then I got Marie Curie fellowship with Dr. Anbuchelvan. I moved to the University of Birmingham. Then after that, so after completing the 2 years of the bioinorganic chemistry, and I made studied different proteins, then metalloproteins for MRI. Then I moved to the University of Hull for this research, and I got a Royal Society grant fund. Now I got another postdoctoral fellowship, and I'm doing now. So this I'm very glad and very thankful to all the agencies, I mean funding agencies and organizations who helped me to do this wonderful work, and all they made up to this level. So there are Royal Society of Chemistry and Newton Baba and Marie Curie actions and FCT and UGC and CSIR. So thank you very much for your attention. Thank you very much. Hello. Hello.
Hello, sir. Can you hear me?
Yeah, please, ma'am. I completed.
Sir, someone posting some questions, sir. Can you
Yeah,
check
please.
the chat box?
Yeah, just let them call, ma'am. Just they can let them, because I can't see all the things. Just if they are one by one, if they're asking, then I can answer for them.
Okay, sir. Please, audience, you can clarify your doubts. You can ask 11 questions through audio.
Yeah, Dr. Anbu, this is Dr. Singaram from Dindikal.
Yeah, excellent, sir.
Yeah, I have a small doubt that why gadol, in case of all the lanthanide elements, why gadolinium is particularly used for MRI?
Yeah, gadolinium is, I said already, it's due to their magnetically active metal when compared to the others. For example, I said that gadolinium has 7 unpaired electrons in their outermost orbital. Though if there is any element with any unpaired electron that is highly suitable, that's why the manganese and gadolinium is highly suitable than the other metals. So though we can use the iron 2+ and cobalt and other like a cobalt and nickel also, but they cannot use directly. We can use them as a chest, but they are not yet clinically available. So only this gadolinium complex is only available.
Yeah, another one. If there is any correlation that due to whether the transition metal complex elements having half-filled configuration can be used for MRI reagent?
No, we can't use except the manganese. The manganese only it is possible. We can't use any other metals. It's not used. We can't use that.
Yeah, thank you.
Yeah, even manganese has only one complex is available at this date. There was 2, that one was now they are not using. They are not using the only one complex that is called manganese chloride only they are using. Hello.
Good afternoon.
Good afternoon.
Sir, you can show 4 example of clinically available MRI.
Yeah.
How they interact with body, how they works in our human body.
I said is the molecule, if we are sending inside, they can interact the water molecules from the body. The water molecules of the tissues get magnetized. So because of the getting magnetization, they will absorb the radio frequency radiation according to their different environment, and particularly tissues environment. Then they will show that difference. They can precise in different frequencies. then they will show the clear image of normal and abnormal cells.
Okay, sir. Which is mostly used in now? Which example is mostly used in now?
No, there are all the compounds are many compounds are they are useful. I mean, more than 10 compounds are useful now, and all, we can't say exactly which one. I mean, some compounds are specialized to diagnose a liver, something for specialized to diagnose kidney, and something specialized to brain, or like that. So we can't say exactly which one is most frequently used.
Okay, sir. Thank you, sir.
Thank you.
Dr. Anbu?
Yeah, please. Yeah.
Can you hear? I am Dr. Senthil from Udumalpet.
Yeah,
so I want more clarification. So I understand that the gadolinium is because of more number of electrons, it is being used rather than using this nickel, cobalt, and iron. But still,
Yeah.
I do not understand very.
Sorry, I think these both metals are directly usable because of their magnetically active metals. That is the main reason. And also the main reason, another reason is the number of electrons, particularly these electrons are they are able to form the complexes when compared to the other metals. Particularly these are less toxic when compared to the other metals. That is also other reason.
Hello.
Hello.
Hello, sir. Good afternoon, sir.
Yeah, good
Hello.
afternoon. Please.
Sir, actually, proton NMR and carbon NMR we used to do for drugs also, sir, characterization.
Yeah.
So, can you explain, sir, how to write that? That means structural analysis by seeing the spectrum, proton spectrum, carbon NMR spectrum.
Okay.
Structural, can you explain, sir? It's very difficult, sir. Some of the peaks are present, some of the peaks are not present. That is more confusion, sir. So, can you explain?
Yeah, it's maybe I mean each proton resonances resonate according to their chemical environment. I mean,
Okay.
the both
Okay.
side, what are the chemical environment? I mean, how many protons, whether it may be a CH2 or it may be a different electrophilic or
Philip.
repelling oxygen or electronegative atom protons or something. If it is according to the chemical environment, it may be aromatic or aliphatic. According to that, they'll undergo, they resonate. So then the resonate will give you a delta values, the chemical shift values. Then from the chemical shift values, then we can find we can elucidate the structure of the molecule. That should be read by the step by step spectroscopy, NMR spectroscopy. Then you will come to know exactly the science behind the NMR.
Sir, one more, sir. Can we get, sir, that means in our compound, 4 protons are there. That means 4 hydrogens are there. Will you get the same four hydrogen peaks in the spectrum, sir? Proton spectrum?
Sometime, if maybe the 4 protons in the same kind of environment, you will get only one signal. If you are getting 2 environments, the 4 protons are situated in the 2 different environments, you will get only 2 peaks. So according to their chemical environment, according to their neighboring atoms, then you will get only the peaks.
Only two or one. Exactly 4 we cannot get.
You can't get. You must read. I think I recommend you
Sir,
to read the
okay,
books.
sir. Okay, sir. Thank you, sir. Thank you very much, sir.
Yeah.
Hello.
So if you want, you can call me separately. Then I can.
So I got doubts, sir. Actually, for structural analysis, if before all the protons are not present, means we cannot confirm it. But most of the papers are confirming this compound is structural analysis. More compound on the structural analysis correct, sir. They are telling the correct. That's
Okay.
confusion, sir. So only.
Don't worry. Don't worry. Just you wanted to read then, but I admire your
I have
curiosity,
got through, sir.
but that will be just you
Hello.
can.
By
You,
showing two peaks, by showing two horizons, they are confining this structural analysis, okay, and putting the papers. So only I'm
yeah,
getting doubt. Sorry,
yeah,
sir,
yeah.
if it
Okay.
is any
Thank you.
wrong
Thank you
in
for
my
your
doubt.
curiosity. Oh, thank you. Thank you.
Thank you, sir.
No problem.
Hello.
Yeah. Tell me, dear.
Hello, Dr. Anbu. I am
Yeah.
Dr. Anupal calling from Portugal. As you know, we are colleagues, work together.
Yeah. Yeah.
So
Please.
your presentation was very good. I got to learn new things. Although we are working in the same kind of field, but you have moved to a different direction now, and it's really nice to see your presentation. I enjoyed a lot. I
Thank
just
you.
would like to raise one question, like you have used manganese instead of gadolinium.
Yeah.
So can we use other transition metals which have similar kind of properties or similar kind of behaviors to increase the relaxation time in MRI contrasting agent?
No, that is not possible here. Only we can use the manganese, only we can use, but we can use the iron 2 plus and a cobalt 2 plus and nickel 2 plus complexes that we can, if maybe sometime they are useful in the chest, para chest, I mean chemical exchange saturation transfer complexes that can also offer the MRI image. But we can't use beyond that. These three are majorly useful. I mean, even though these agents are not still yet clinically not available.
Okay, and one more question, like while doing the MRI analysis or MRI
Analysis,
analysis,
yeah,
yeah,
relaxivity
analysis,
study.
like how do you administer the drug? Do you do it orally or like in the form of solution or something like that?
No, we have to inject. I mean, before that, we have to do the, normally we have to study through the NMR machine. Just we can use the NMR machine and we'll study use the different program, and we can run the relaxivity, and then we can get the relaxivity values. Then after that, we can think of whether maybe it's showing the high relaxivity when compared to the other complexes, already reported complexes. Then we can go further. Then we can inject if maybe sometime all the compounds which are showing NMR machine itself, they are showing high relaxivity, means they are not necessarily should show the high enhanced image in the in vivo also. So sometimes it's we are getting negative results from that. So first we have to try in the NMR machine, then we can get clear then what is the exact relaxivity value, then we can go for beyond that.
So in that case, I think we need to find out the toxicity levels of the compounds
Yeah,
also.
that is important. That is important. Sometimes we can maybe there is no possibility to do the in vivo MRI, so we can test with some our like a normal in vitro cell studies, then like at cytotoxicity studies. Then we can get what is the toxicity of the compound, we can come to know. Then we can go further. If it is showing potentially highly useful as a probe in the magnetic resonance imaging, then we can go for that.
Okay, thank you so much.
Yeah, thank
Okay,
you.
all the best.
Yeah, thank you, see you.
Hello, sir.
Yeah, thank you. Yeah, please.
I am Dr. Pramila speaking from Arulmigu Palaniandavar College of Arts and Culture.
Okay, ma'am.
I have a doubt, sir.
Okay, ma'am.
A mammogram is frequently used for diagnosing the breast cancer. Can you
Yeah.
tell me what is the technical difference between both things, MRI and mammogram?
The mammogram is the base is working based on the X-ray. The X-ray is the base of mammogram. The mammogram is taking the photography of the deposited phosphates in the breast. So sometimes there is a some depositions, some flakes, and those kind of materials are formed if maybe there is the cancer already in the breast. So then we can get very clear image by using the mammogram. So we can first diagnosis, if you're using the mammogram, then we can get clear cut of that whether there is a cancer cells or not. Then that is the method that is the initial method they are using to diagnose the breast cancer. But here and MRI is very different. It is not using any harmful radiation like X-rays. So here we are using only magnetic energy and radio waves. That's all.
Thank you, sir.
Yeah. Thank you.
Hello. Thank you, sir. Thank you,
you.
audience. We have posted the feedback form in the chat box. Please fill the and also join us tomorrow. Thank you, everybody. Now, Mr. Shanti will be presenting the vote of thanks. Please, sir.
Thank you.
Hello, Shanti. Are you here? Hello.
Hello, can you hear?
Yes, Shanti.
Good afternoon to all. It's my privilege to deliver a vote of thanks on this occasion. First of all, I would like to express my profound gratitude to our principal, Dr.Anbuchelvan, for her continuous support and a lot of encouragement to organize this 2 days international webinar. Thank you, ma'am. On behalf of management, principal, and faculties of physics department, I express my heartfelt thanks to our chief guest, Dr. Anbuchelvan, for kindly accepting our invitation and delivered a lecture on science behind MRI. Today's lecture was full of knowledge and informative, and the way in which he explained this topic was extraordinary. Thank you, sir. It's my immense pleasure to thank our HOD, Mrs. P. Umarani, for her support and guidance. I extend my thanks to all the participants from various colleges and universities for their presence. Thank you, one and all. Thank you very much. Stay home, stay safe. Thank you.
Sir, thank you, sir.
Thank you, ma'am. Thank you.
Thank you very much, sir.
Thank you, ma'am. Thank you.
Sir, presentation was very nice, sir.
Thank you. Thank you.
Good morning.
Actually, it starts from the fundamental and you go to even the advanced techniques, sir. It's very nice.
Yeah,
Many
thank you.
posters like that also, sir. They experience like that.
Oh, thank you.
Thank you very much.
Thank you, ma'am. Thank you.
Sir, please join in tomorrow's session also.
Sure, definitely, ma'am. Thank you. Definitely. Thank you.
Oh, thank you.
Thank you.